Hello everyone. I'm just laughing to myself because my internet connection went down about 5 minutes ago. But it's okay, it was entirely temporary, it was just a matter of restarting my modem and everything was fine. So, not a big deal. Welcome back. Good morning. If it is the morning for you, it's probably not the morning for most everyone who's in Sydney at the moment. I've shifted my camera angle today. I've tried to move my webcam and its microphone a little bit further away from my laptop because my laptop tends to sing a little bit. Has a fan that's actually quite loud. Actually, now that I think about it, I should actually just set the fan to silent while I'm lecturing. I've got this little thing there where I can control the fan settings, so set that back to silent. I always forget to do that. Okay, so this week we have been looking quite deeply at what we've been doing with building up pointers, structs, memory allocation into linked lists, and we're going to be continuing that today. If all goes well, we will be able to complete our Battle Royale example to the point where it's actually playable. We'll see how we go with that. I mean, what I'm noticing, I'm getting a few questions and stuff looking at the forums, is that there is a little bit of this point in the course being the culmination of tying everything together, which means that if people are missing a little bit of understanding in parts of things, it's much harder to construct something out of it. So I may try to just sort of ease back on the tempo a little bit today, which means I might push some of the demo further into the live stream tomorrow afternoon. Same time tomorrow. We're going to do a live stream same time tomorrow. I do want that to be about the assignment, but honestly, the last 3 lectures of building this Battle Royale example has basically been me doing something that could have been the second assignment. So it's very, very similar, but it's not everything. It's obviously not everything. It doesn't have any of the hard bits. But it does have a lot of the main bits that are going to be similar in the assignment. Speaking of the assignment, I hope everyone has, at minimum, looked at the spec and had a chance to kind of at least see what you think about it and what you think you want to do with it. What was I going to say? A few people have already started. We were a little bit late getting all of the tests going, so we're actually going to be writing our own tests in the assignment. So you'll see that there's more than one file that has a main function in it, which means you can actually compile 2 different ways. One is the actual interactive way of running it, like you're running it like a game, and there's another way of running it that allows you to run an automated testing thing that just picks out individual functions one at a time from your CNH files and sees whether they work on their own or not. So there's a little bit of interesting stuff going on there. I should point out that we did change something in the assignment after it was released. So that was just yesterday. We realized that our auto tests and our reference solution was doing something slightly different from the spec. So we've actually changed the spec to match that, because I think a lot of people have already written code to fit the auto tests, and so we thought that the mistake in between the two, we should change the spec to the auto tests. This is only in the text searching part of it, so this is only anyone who's gotten up to stage 4 or 5 already. So we're assuming that this is not affecting a very large number of people. Actually, we can kind of see, because we can see everyone who's been running auto tests, so we can see that it hasn't affected that many people. But if you've already completed code, it still works. If you haven't gotten up to it yet, you may want to just read it carefully to make sure that the spec hasn't changed too much from what you originally believed. Chat's pretty funny at the moment. There appears to be an argument going between snake case and camel case. I'm going to hopefully try to make sure that that's not really an argument by constantly going back and forth between the two. You can kind of tell that I naturally do camel case, because you'll see me do that on instinct a lot of the time, but I'm going to at least try to make a significant number of the examples that I do in the course in snake case as well, to let you know that you will be expected to be able to jump between the two of them depending on what the style is of the code that you're working in. So if you're working in an organization or a company or something like that, and they already have a style, they're very much going to expect you to follow that style rather than create random inconsistencies in like small individual files here and there, which is something that would be kind of hellish to have to read if you're like, why is 3/4 of this file in snake case and then 1/4 of the file in camel case? It's really like, it's off-putting to see that. So what we'll try to do is every time we do a project, we will stick to one particular style, and that style must be consistent through the entire project. When you get up to larger scale things, you might end up in a situation where that scale becomes it's not scale, case. I just mixed up saying snake case. Yeah, but when you get to a larger scale of an organization, it might be that the entire organization is always in one of these styles. So get used to being able to switch between them. I even suggest, if you want to, switch between them in your lab assessments so that you can do both naturally. I mean, it's not that hard, because this is just phrasing for things, like in terms of whether there's spaces between things or not, but it's worth practicing everything so that you know everything. In the wise words of a one of the very first internet TV series, Pure Ownage, back around the turn of the century, that in order to truly own, you must own at all games. And that's the same philosophy I like to put into programming, is don't get caught up in a single language, don't ever get caught up in a single way of doing things, because that's always a trap. If you end up with only one technique that you can do well, at some point in the future that technique is going to get superseded by something else, and then you'll be left with nothing. Whereas if you learn the basics and you say, oh, I can adapt to any situation. So I may want to get into an argument on the internet about which case is better, and if that's your if that fries your burger, then yes, you can go and make arguments about whether snake case or camel case is better. I refer to Exhibit A, the live chat at the moment, is the conversation between snake case and camel case, but I say that regardless of which case you're in, you should be able to succeed with both. And I'm not saying you should be able to succeed with just the one that you're using at that particular time. You should be able to go back and forth between them and have full success. And that's going to be the case not just with snake case versus camel case. This is also going to be a situation where you get into let's get into an argument of like C versus Python or something like that, and I'm going to say that whichever one you like more, you probably want to put a whole lot of practice into the other. And then you'll be able to work with both. I should heed my own advice, actually. I'm really rusty with Python, especially because I'm full-time writing C, right? So I just saw like a moderated message there, and I thought I'd let that one appear because that's quite funny from Matthew. Okay. So people are also talking about stage 1 of the assignment, stuff like that. If you are having issues with the assignment, come along tomorrow. So tomorrow, 4 to 6 p.m., I will be doing a look through the assignment, and I will answer any questions people have about, like, say, construction of linked lists and things like that. The tutorial and lab this week is super important for that. Your tutors are going to be going right back to the beginning and building a linked list from scratch. So I think that if you're worried about how to use linked lists, that's a really good thing to do as well. Okay. So let's get into the content. I am going to start off with a review of some of the stuff we did at the end of the week. Not the end of the week, at the end of the lecture yesterday. because I always say yesterday for the previous lectures on Tuesday. So let's get into it. So what we learnt last time, we did a little bit of revision. We were talking a little bit about pointers, structs, and memory allocation, because those three concepts are things that we're definitely going to need when we're working with linked lists, because linked lists are built up of structs, and those structs have pointers to other structs. While we're doing that, we're also going to be working with allocating memory for each node in the linked list. So we need to know a little bit about memory allocation as well. There's always going to be two ways that people learn about how to use linked lists. The first way is going to be, let's not think about programming them at all, and let's think about them as an abstract concept. And that's why I've got a whole lot of diagrams, which is like this bubble points at this bubble points at this bubble, they're chained together, and then you get a linked list. As opposed to thinking about them as code structures in memory, which is the other way to think about them. Is like, okay, there's this piece of memory, and inside that piece of memory is the address of another piece of memory, and that's how they link together. And then we get down to the difficulty of let's work with pointers. So I think this is one of the things that trips people up the most, is if I change a pointer without putting a star on the pointer or anything like that, if I just change the pointer, I'm changing where it aims. If I change a pointer and I use the arrow afterwards, that means I'm following the pointer into the struct and looking for one of the fields inside the struct and changing information there. So know the difference between changing a pointer, which changes usually is changing which object it aims at, versus following the pointer into a struct and changing something inside it. So the different things that are going to happen, whether you are accessing the pointer on its own, or whether you're saying this pointer is going to give me the location of a struct and I'm going to go in there and make changes. Those are some of the things that tend to trip people up a lot. Okay, so that's what we were doing before. We did building lists, and we did some insertion into lists. And so we looked at the insertion algorithm. I've got all the slides for insertion again today, so we're going to go back over that. And we started working on alphabetical insertion. Like the code that I gave you last time, I didn't even have it at a point where I was going to test it yet. But we're going to redo, well, not redo, we'll talk through some of it, and then we'll finish the code for alphabetical insertion. And then we will hopefully be able to show a demo of us actually inserting into a list with random order, and then the list coming out in alphabetical order. And we're going to talk through how that works. And then we're going to try to build this up into a full game. Well, it's not really a game because none of the game bits are in it, but a scoreboard for a game where we can see who's currently in the game and who isn't. And people are going to leave the game by being removed from the list. So we're going to do removal today, and while we're doing removal, we're going to look quite carefully at how we handle memory, because if we build a linked list out of allocated memory, if we are going to remove anything from the list, we have to make sure we free the memory from something we removed. Otherwise, we end up with memory that's still allocated to us that we've lost access to because it's no longer in the linked list. So with that, we will have removal and memory freeing, and we should then be able to get to the point where we can complete this entire game example and have this kind of battle royale where we have a list of people and then we remove people from the list one at a time until only one person's left and they get called the winner of the game. Sorry, I just saw a comment from Liang. Give all your variables one-letter names so it compiles faster. Mark told me it's true. I think at some point I mentioned that maybe there would be a tiny millisecond increase in speed in compilation if your compiler didn't have to read as many characters. If any of you start coding with that as your rationale behind things, there's going to be fighting words to be had. So I'm not going to talk any further about that. And I'm still going to be marking you on good variable names. Your tutors are going to be marking you on good variable names. A lot of people are getting some really useful feedback on style at the moment. Don't worry if your style mark wasn't as high as you wanted it to be. Like, this is the beginning. This is the first assignment where you're even marked on style. So what I say is if you think that you could get more marks in style, then go for it. Get more marks in style in the second assignment. And if you still think you can get more marks in style later, get more marks in style in the first assignment in the next subject that you do, etc., etc. Reese is asking if marking has finished. Marking has not finished yet. A significant amount of marking has been done, but I think I don't think we're halfway through the course yet, but I think we're getting close to halfway through the course now. So there's, it's probably less than a 50-50 chance that yours has been marked yet. Some people definitely has been, but not everyone yet. Okay, so what are we doing today? I've actually kind of mentioned already a bit of what we're doing today. So we're going to continue our work on finding something in a list and the alphabetical insertion. So we haven't finished that, so we're definitely going to be working on that still. But then we're going to do linked list removal and freeing the allocated memory that we have for the linked list itself and for any nodes that we're going to remove. And we'll probably do some demos in that as well, look at leak check and stuff like that, and then we'll see if we can get to the point where we can actually play the game. So we can actually say who got knocked out, knock them out each round until we don't have anyone left. Okay. Now let's continue. So, where we were up to last time, and what we hadn't quite finished yet, was insertion with some conditions. So I'm just going to connect to VLab. I don't think I've made a folder yet for lecture 14. So I'm going to make that, and then I'm going to copy the file that we were working on Tuesday into this new directory. So I've got like a snapshot of it at different stages. I uploaded the file already from Tuesday's lecture. If you've played around with it, I mean, there's only been a day in between, but if you have played around with it, you'll notice that it sort of works for certain circumstances, but it doesn't for everything. So that one's really like one of those part-way through things. I mean, that's like one of those things where you could be partway through an assignment and go, I'm just going to submit this. I know that it's not complete. I know that it doesn't kind of work for everything. But that's the submission because I happened to finish the day there and I had to go off and do other things. So that's the kind of thing where you can consider that to be like, it's non-functional, but it's a backup at least of what you're doing. So I'm going to copy from lecture 13 battleroyale.c, and I'm going to copy that into lecture 14. So now if I go into lecture 14, okay, tab completing there just to speed things up, and here's what we have from last time. So to remind us of what we're doing here, we have a series of functions that we're using. Someone pointed out to me, I think it was on the forums, because I think Dean, you passed this on to me, that I had swapped the input order on these, which is not necessarily going to change the way that this function works. Like, the input order doesn't change what variables are created or how you can use them. But it's nice to be consistent with these things, and I realized that I had set up an order of inputs here, and then I changed it here. And so what I might do is I might flip these back around. This is purely style here, what I'm doing. It does not change the way this thing functions. But what it does is it means that every time I call one of these functions, I kind of know that the name of the player is always the first input, and then a pointer to the list or to something else that I might be doing with it is the second input. So it just makes it a little bit neater in terms of style to have these in a similar layout. Echo is wondering why I changed the two of these instead of the one. I don't have a particularly good reason why I changed the two instead of the one, other than this one came first, and so I allowed that one to be the first one. I could very easily have changed that one instead of the others. I think the other reason was, if I remember correctly, I think I had set up a convention in the slides as well. I'm not necessarily really using the code slides, the code that's in the slides. What I like to do is I like to write it from scratch in front of you so that we can talk through the process of writing it. So I don't like to copy down what's in the slides. So what's going to happen a lot of the time is that the code that we actually write is actually going to be different from the code that's in the slides, because I prefer to actually construct it as we go. And if people give me comments on things, then I might change it as well. The other thing, if I've changed these lines, then these lines also, the first lines of these have to change. So I'm going to do the same thing here. Here. And also every time I call it, I need to be calling the right thing. Okay, so all of these are now need to be flipped. Not that I'm going to be keeping these, actually. I will be pretty soon wanting to replace these with alphabetical insertion, but I'll just make sure that my code probably works at this point before I do anything else with it. Okay, so that was me just doing what we actually call, in the biz, we call this refactoring. It's not exactly refactoring, but kind of, where we change the layout of things without changing what actually is the functionality of the code underneath. Yuji's asking about A2I versus string to long. Dean, I'll let you answer that one. It's not actually a huge difference between them. That's an interesting one, and I think we should take that further, Yuji, but we can't do it right now because I've got content that I need to deliver. But I think that's an interesting question, that we should test the difference between A2I and string to long. Because I was pretty sure that string to long was going to give us a good result for everything that A2I could do. Because I thought that string to long was a kind of a superior function to A2I. A2I had less safety checks and stuff in it, but I'm interested to see the examples that you can show to see the difference there. But anyway, I'll move on because I don't think I want to necessarily get into that conversation right now. Okay, so let's go through the functions that we've created already and have a look at what they do. So create player was a reasonably simple function. What it was going to do was allocate memory for the player, and then set up the player's name in that memory, and then set up the next pointer based on what we were given in that memory. So P is a pointer to that memory. So P, using the arrow, says I'm going to follow that pointer to the memory, and I'm going to look inside for the field name, and I'm going to change it to input name. Likewise, follow the pointer P into the struct, find its next pointer, and change it to whatever address we were given in input next. So reasonably simple. We then had, assuming that we actually had a linked list somewhere, a way to print out the names of all the players in the linked list. So we assumed that this was a pointer to the whole list itself. We made a copy of that, being the current. We don't always have to make this copy. We could have used the player list pointer through here, because this is such a simple function that we didn't need to maintain the pointer to the start of the list as we have here. Having said that, I tend to do this because a lot of the time we don't want to overwrite this pointer as we would here if we were looping through. So sometimes we want to keep a pointer to the head of the list for other purposes. So on instinct, I just created a new variable to say this variable's just for this loop, and that variable might be used again somewhere in this function. So while loop, this is the standard while loop to go through a linked list, where it says if the thing I'm pointing at the moment is not null, then I will keep going through. So I will be, if it's not null, then I will be able to access its name. If I can access its name, I can then print out its that string to the standard output. So that's what fputs is doing. Fputs takes a string and sends it to standard output. Standard output is this terminal here when it's running. And then I'll put a new line on the end of that just to format it nicely. And then the while loop then moves on to the next node in the linked list by saying, what is the next node from the one I'm looking at now? Replace the pointer that I'm using to move through the list with that memory location rather than the current memory location. So it's kind of like I've got multiple memory locations, and each one tells me where the next one is, and so I move my pointers between them. So current equals current next is saying whatever my current pointer was, follow that into its next, and that's into this location. Now move the current to that location. So this while loop will keep going along until that current goes off the end of the list, and if the memory I'm in there has a pointer to null, then current will then be null. It will then stop running the while loop. So this is how we're going to loop through linked lists. This is the most basic loop that's going to look at everything in a linked list. So I would try to get the idea of this line and this line in your head, because we're going to be using them a lot. Anytime we have a linked list, there's a really, really good chance that we're going to want to look through all of the items in the list, or at least start walking through the items in the list and stop at a certain point. We had code for insertion, and the code for insertion was actually reasonably small amount of code. But remember, I was talking about the monk going up the mountainside and meditating for 20 days just to cut a foot of wood off a stick and say this one is now superior. This is the kind of world we're in now, with this kind of logical and abstract thinking about our computing. And this is the kind of thinking that will get you through being able to do things in many different languages. If we have to do a lot of thinking and only write 2 lines of code, then you know that a lot of the work is not really in the code itself. It's in figuring out what it is you want to do. So this comes back. Oh wait. I didn't actually have the insertion code. I only have the finding the insertion point. So let's just go back to it. Hang on. My lecture slides, lecture 13. Okay, there we go. I was like, am I about to give away something confidential by opening my Google Drive? But it wasn't too bad. Okay, so insertion code is here. So before we've inserted anything, we've just got these 2 nodes. Then we create a new node, so we can do this with the create player function. Then, to link this up to the second node, we say, okay, copy the first node's next pointer, and then we'll be aimed at the second node as well. Because the only way we can find the second node is to use the next pointer of the first node. And that's this line here. So the insert position was the first node that we're inserting after. And so what we do is we say, this thing's next pointer, we want our next pointer to be aimed at the same thing that that thing's next pointer was. So we insert ourselves into the chain. And then we say, all right, now that we're linked to this node in the chain, we can link the first node to us. So we can say, okay, take the first node's next pointer, which is here, the insertion point's next pointer, and point it at the new one that we just created. So the new one we just created, we have a pointer to it because create player, when it creates a player, gives us back a pointer. And for the moment, the way that we're doing this is we're returning a pointer to the player that we've just created, just in case we're inserting into a list that didn't exist before. If we're inserting into a list that didn't exist before, this code here doesn't run because the insert position is null, in which case we want to make sure that someone knows that we've just created memory here, and so we give the pointer back to it, so we don't lose the piece of memory we just created. That's in the case where we were going to make a new list out of nothing. Alright, so from there we get to where we're up to now. So let's go back to the current slides, and we are inserting into an ordered list. And so the interesting thing about inserting into an ordered list is a list with no elements in it is ordered. A list with no elements is in perfect alphabetical order. And then a list, when we insert one element into it, is also in perfect alphabetical order, because something can only be out of order if there's more than one element and they're in the wrong order. So what we can do is we can assume that if there's nothing in the list, it's in alphabetical order. If there's one element in the list, it is also in alphabetical order. Then when we start inserting things into the list, we make sure it's in alphabetical order by making sure we insert before or after the things that we're supposed to insert before or after. So we're going to write code that makes sure we do that using this string compare function. So string compare is going to allow us to look at the names in the strings and say which one is before or after the other. And what we're going to do is this kind of thing where we're going to loop through, and we're doing a loop that is not trying to do something to every node. So sometimes we would do loops that we're trying to access every node. So for example, the print players is trying to access every node and print out the name of every player in the list. This thing isn't. This thing is just looking for a point where its word is in between the one before and the one after. So every time we see a letter that is earlier than us in the alphabet, we keep going. When we see a letter that's after us in the alphabet, we stop and we say, okay, we've got to insert before this one. Inserting before this one involves calling our insert function on this node, because our insert function is an insert after. So what we do is keep track of a pointer here and a pointer here, and we move those two pointers along. And when we find the right spot, we know that we should be after this one and before this one. So we insert after this one, and then it goes there. In fact, if I wanted to make this really really readable, I might actually use the name insert after, because then it's really clear about what I mean with this insert position. So I could make this more readable by saying insert after, and then I can come up here and make sure this says insert after. I'm going to copy that. Just make sure those also say that. I may not be using these again, actually. I'm probably going to be deleting them once I've got my insert alphabetical going. But I've just realized that I could make this more readable and more understandable if I call it insert after. So I have a position in the list, and I'm going to insert a new node after that position in the list. Unless that, of course, is null. And if it's null, then I will just create it and return it. Okay, so if I'm inserting after, I'm having two pointers. So first pointer, struct player pointer, is the current. The current is the head of the list. So this is looping through. This is really similar to this loop through here, where I said the current is the head of this list. Then the trick I'm doing there to trail a pointer behind the first one is to have the previous pointer. So there's the current pointer, it's the one I'm currently looking at, and the previous pointer is the one I looked at just before. And so the way that these two are working in this while loop is they're doing this little leapfrog, well, it's not even a leapfrog thing, this little catch-up thing where I have my current pointer and it points at one of the nodes. My previous pointer copies my current pointer. So previous equals current says I'm going to copy the current pointer, which moves the previous pointer to the same location as the current pointer. And then the current pointer says current equals current next. We've seen that before. That means current moves on to the next node. So we've got this movement of these two pointers like this, where the previous always catches up to the current, and then the current moves on to the next node. So after this while loop runs, they're on two separate nodes. Current is on the first node that we found that caused this to fail or this to fail. So either current is aimed off the end of the list, or current is pointing at the first element of the list that should be later than us alphabetically. And then what we can say is, let's insert at the position of the previous. Now I need to make sure I'm calling the right function here, because I've just made a whole lot of changes to it. So it was insert after, and the name came first, and then the position came second. So input name first, and then the position is previous, because it's insert after. So if I want to insert it between previous and current, it inserts after the previous. So it goes in between the two of them like that. So when I'm in this example here, if I've moved up to this point, my previous pointer will be here, which means I'll have the previous pointer and the pointer, and I know I want to insert in between the two of them. If I want to insert after this one, called previous, I can call insert after and put this pointer in, and then I know my node is going to go in between these two in this list. Okay, so we've got that so far, and one of the nice things is all of our functions are not super complicated because each function's only doing one little task, right? So our first one is doing the memory allocation. That's it, nothing else. And then print players is separate because we're not using that for this particular chain of functions. But insert after is doing one thing where it says, okay, mostly all I'm going to do is move some pointers around to insert one node between two. And then this one is saying, okay, I am going to find a specific position where I want to insert by looking for this alphabetical order thing. And then I stop my loop at a certain point. When I stop my loop, I've got 2 pointers. And then I say, okay, insert after the previous pointer. And then I'll be able to insert a node in between the two of those. So what we've got at the moment is we have the capability to, if the list is already ordered, we can then insert elements into that list and they will go in the right place. We could potentially test this right now by setting up a list that's actually ordered. So at the moment this is putting chicken as the head and then me as the one after the head and then Frankie is the one after the head. Let's just run this. I'm going to call it Battle. I could have called it Fortnite. Missed opportunity. So what I'm seeing here for the moment is not too bad, is that this is in alphabetical order. So if it's already in alphabetical order, I can test my insertion to see whether it's capable of inserting into this list in alphabetical order. So that list is in alphabetical order, so I'm going to go test alphabetical insertion. It's funny when I start typing comments and I just start typing normal English words, I just like typos come out all through my work. And so when I'm typing code, it's always like highly accurate, but like English language is where things start to lose out. Okay, so testing alphabetical insertion, I'm going to do insert alpha, and I want to insert a new player into this, and so I want to test whether a new player is going to end up in the right place in the list. So Dean's here at the moment. Let's insert Dean into this list. And then I might just do a printf in between. So this is just testing stuff, right? This is not important for what my final output should look like, but this is me testing to see which bits of my code are working. So it's very often that we'll use things like this to be able to okay, let's just have a look at whether this thing's working or not. As you get into more complex things, this might actually be in another program. You know, in another program that just calls these functions and sees whether they work. Your second assignment is going to do that. Anyway, so printf testing inserting Dean into the list. And so after we've done that, I'll print players again using the head of the list. I'm assuming for the moment I'm not changing the head of the list. I know because this thing is not capable of dealing with insertion at the head of the list yet. So what we'll do is just test, and what I'm hoping for is Dean comes between Chicken and Frankie here because his name starts with a capital D. So let's just see if this little test works, because the rest of the code's not entirely going to work yet. There's several ways we could break this code at the moment. It's not complete. So let's compile that again and see whether this sequence of things that we're doing works. So we had Chicken, Frankie, Mark, testing, inserting Dean into the list, then Chicken, Dean, Frankie, Mark. That's pretty good, right? So I know that my code was able to identify where in this list Dean should fit based on that string compare. So it said that Dean was, well, D, the capital D for his name, was in between the capital C and the capital F. I mean, it's able to compare the entire string, but we can actually just look at it with the first letters because we know at least a little bit of where of how the alphabetical ordering should work. So we know that this insertion is working. We could try other things, and so I'll show you how we can break this. Do we have any of the tutors whose names start with A? Oh, Anusha's name starts with A, so let's try to insert her name into the list, and we'll probably see this break at this point because I know that insert alpha hasn't at this point been able to deal with inserting to the first element of the list. So let's compile this and run it and see what happens. Ooh, interesting. It hasn't crashed, which is maybe a good sign, but it definitely hasn't inserted the new player Anusha into the list, which should have come in before Chicken at this point. So what we have is a situation where if my insert position was the first element of the list, I need to do something different. So something else has to happen here. So we need to think about what conditions we're going to be in if we're trying to insert at the start of the list. So insert at the start of the list. What can we check from our previous code that gives us an idea that we should have been inserting at the start of the list? So if we have a look at this, we say current starts at head, previous starts at null. If this thing never runs, it means that we should insert at the start of the list. So if that never runs, it means either the first thing we saw in the list was after us in the list, which is the case here, or the list was empty. So either way, if either of those situations happens, the while loop never runs, we're at the start of the list. So we should check for a certain condition to see if we're at the start of the list. And I've got a really easy one here because I know that if previous is equal to null, insert after can deal with null, but it can't necessarily use that at this point. So if we're inserting at the start of the list, then what I'm saying is I know that I'm at the start of the list if the previous is null. Because if the previous is still null, it means this thing never looped. If it did loop, the previous would always be moved to at least the current. Yes? These are important things that people are learning. Someone wants to point out things that are happening. I'm just checking what's happening in chat while Chicken says hi to everyone. Hello. Wouldn't it be better if you make the names capitalized even after we put int in small? So Andrew is wondering about the capitalization of the names here. I think it should be okay with string compare. It's going to be different if we have a lowercase letter for an uppercase letter. So if I wanted to be really, really strict about proper alphabetical order, I would probably allow lowercase letters to be compared to uppercase letters. But for the moment, I'm not going to bother. This is just an example showing things. I think if you wanted to, like, we could spend 2 hours just on alphabetical ordering. So I'm just going to keep it simple and just go, look, we're just going to have one test for this, and we just use string compare. Okay, so what I have here is I have something that tells me if I'm at the start of the list. So if I'm at the start of the list, then I know that my insert after hello. is going to be the new head of the list. So this is something that's interesting. And remember last time how we had a pointer to the head of the list and all we did was return that pointer without ever changing it? Now it's going to be different, because now if I'm inserting to a null and I'm intending this to be the start of the list, then what I'm going to say is the head is now going to be equal to the new node. Got to be careful here though. Got to be really careful, because if I do this, I've just overwritten the head of the list. If the list exists and it's got a whole lot of items in it, I've just made all that memory disappear. So I've just caused a massive memory leak if I replace the head. So I've got to be careful not to necessarily replace that head until I'm sure that there isn't necessarily something in it. So what I might do instead of replacing the head is I'm just going to make a new pointer. It might be temporary, but I'm going to make a new pointer for this one, and I'm going to call it new head, because it's likely to be the new head. I'm wondering if I want to do this slightly differently. No, it's okay. We'll roll with this and we'll see where it goes. Okay, so this is the new start of the list. The new head of the list is going to be whichever element I insert into null. And the reason why I know this is going to be the new element is my insert after function says that it will return a pointer to the inserted node. So it will always return a pointer to the node that was just created, which means I know, or I can use its output to say, this is a pointer to the new thing I just created. Especially if it's null, it doesn't automatically connect it to a list if previous was null. So here previous we know is null because we've tested if it's null before we did this. In fact, if I wanted to, I could just go like this. I could say, look, it's null anyway. I don't need to pass a variable in, I know it's null. So I could say, I'm inserting into no list. The list does not exist. And so this is like I'm creating a new creating a new player. In fact, looking at this, I could skip insert after entirely, and I could call a function that's elsewhere, and I could just say create player. And this is going to make this more readable as well, because it's like it's not inserting because I'm creating a new element to be the new start of the list. So I could do this, create player, and we start off with the name, which is input name. And then the next thing was going to be whatever the next of the of this new one is. And one of the good things about this is if I know that I'm inserting at the start of the list, if I know that this element needs to be the first element of the list, I can actually do this. So recall what create player did. Create player puts whatever name you give it in, and then makes its next pointer whatever pointer you give it. So if I do create player where the next pointer of the thing that I'm making is the head of the list, if the list has other items in it and stuff, then I insert myself. Hang on a second. Let's show you what's going on here. Right. So let's say we've got the list that we had there. I'm just going to go with the first letter. So was it chicken, Frankie, Mark? And then we've got a new one here that I've just created. That was Phoenicia. So we've got this here, and we want to insert this alphabetically into this list. So we've got a head pointer there, and we've got our current and previous. The previous is pointing at null, and we've tested the A against the C, and we've said, oh, okay, we actually need to put the A in before the C. So if we're going to put the A in before the C, A is the new head of the list. So what I would do is I would put a new head pointer here, and then the next of A would be a copy of that old head pointer, which would mean that the next of A would be pointing at the same element there, and then this new head pointer here, so this is head, and this is new head. This one here, so I've got an icon. This one here is the one that I return, and I say, okay, after I did my insertion, so returns are pointed to the head of the list. So after I do my insertion, if there's a new head of the list, then that is what I return at the end. So I'm going to actually return this new head at the end, rather than always returning the same head of the list that had been there before. So this line here does this, where it creates the new one, and it says the next of the new one is whatever else was at the start of the list previously, whatever's the head of the list. This also works even if this head was empty. So if this head was null, then the next of this is null. It's still a perfectly functional linked list like that, because every linked list ends with a pointer to null. So if this list didn't exist, we'd have a pointer to null at the end of our new head of the list. And so if we've done this, we want to return the new head. So we could do this here. It's a little bit like it's possible, and it's sort of okay. A lot of people will do returns like this, but it can confuse people really easily, because if I returned new head here, it's not really entirely clear that the function might end here or it might end here. And so what I will often do in this case is I will make a new player pointer here called new head, make it equal to the head of the list. If I'm inserting at the start of the list, then new head will change. It won't be head anymore, it'll be something else. It'll be whatever was created with create player. But no matter what happens, I will be returning the new head of the list. So this way, like, sometimes I prefer doing it this way because you can just read it all the way down to the bottom and you know that the function always makes it to this last line, as opposed to putting a return partway through, which you can think of logically. You could potentially do it, but you don't necessarily want to always have returns in between functions. So this is just a structural thing. So now we have a situation where if we wanted to insert at the head of the list, we could do so. We would create the new element and say this new element is definitely the head of the list that's going to get returned. And then it connects up with the rest of the list, wherever that is. I think now I am able to do insertion at the front of the list as well as anywhere else in the list, but I haven't tested to see whether my inserting at the end of the list is definitely going to work or not. So let's do a little bit more testing on this to see if it works. So we had Anusha at the front of the list. Dean's been removed. Someone said we forgot Dean, I think. So at the moment, Dean has been removed there, and so we'll do another insertion. So we'll do another alphabetical insertion. No. Come on, chicken. No. She's actually sitting on my keyboard right now, which makes it harder to teach you about programming. Okay, let's do another insert alpha. And this one we want to come in after everyone that's already in the list to see if we can insert at the end of the list. So I've got someone who's going to fit there. Tom will definitely fit there. Another thing that we probably want to do, and we want to be careful about this because insert alpha has a certain thing, all right? Insert alpha returns a pointer to the head of the list, even if the head of the list changes. So we don't want to run insert alpha without taking its output. So we might lose its output and lose the new head of the list if we don't take it. So what we're actually going to do is set the head of the list to the result of insert alpha, so that if insert alpha needs to change what the head of the list is, we've still got it stored here. So now every time we do insert alpha, we give it the opportunity to give us a new head of the list, a new pointer to the start of the list. So I mean, like, when you think about it here, we don't want to use this head pointer anymore. This head pointer is now pointed to the second element of the list, which is not something we're interested in. We're not really ever interested in the second element of the list when we're passing the list around. We're always interested in the first element of the list here. And so if it's going to give me a new head, then I want my variable here, which is the list that I'm using, I want this to always be the current first element of the list. So that's why I replace it with whatever insert alpha tells me. So we insert alpha with Tom, and then we're going to say testing, inserting Tom into the list, and we will also print players. And now, you know what I'm actually going to do? I'm not going to leave Dean out of this. I will also insert Dean into this list. So now I'm going to have three insertions. people are glad that that the Dean's coming back in. Oh, actually no, they're glad that the Dean's actually helping them teach stuff as well. Okay, so we're going to insert all three of these into this list, specifically knowing that Anu should be at the start of the list, Dean should be in the middle somewhere, and Tom should be at the end of the list. This is how we do testing, right? This is how I test whether my functions work. I'm testing if they work under several different conditions. Okay, so let's compile that again, run it, and see what happens. Okay, Anusha got inserted at the start of the list. Perfect. Good. So we know we can insert at the start of the list. Dean inserting into somewhere in the middle of the list works. Inserting at the end of the list with Tom worked as well. So now, this is really cool. We now have the ability to insert alphabetically into the list, knowing that anything that we can do with alphabetical insertion is probably going to work. So now that I don't need this testing anymore, I'm going to remove a lot of the printfs and stuff out of this, and I'm just going to grab my list of players. I'm going to put that there, but I'm also now going to be using insert alpha for everything, because I want all of my insertions to be guaranteed to be alphabetically ordered. So now I've got this whole roster of players in then. Eugene saying yes, at the end the tutors will be battling each other to knock each other out of the round, and they get to play again. It's not actually the movie Battle Royale where people actually have to die, and it's not Hunger Games or anything like that. It's just a computer game. Alright, so knowing this, with this insert alpha, is going to make sure that all of these get inserted, and they'll all check where they should insert, so that they'll all insert in the right order. So hopefully all 6 of these, once we insert, should be inserted in the right order. So let's just actually make sure that that's working. I'm pretty sure it's going to work because I've done my testing, you know, but let's see. Okay, so Anusha, Chicken, Dean, Frankie, Mark, Tom. Sweet. Okay, so everyone's saying Chicken is 100% walking away with a win. I'm pretty sure that's going to happen as well. It's more about the order that the rest of us managed to, like, who gets to challenge Chicken is the key. Okay, so now we've got alphabetical insertion. So we've gone through a lot of this different stuff with moving pointers around, creating items and stuff like that. And now we have the ability to do, we've written an insertion function that can insert, always knowing that the insertion will happen in alphabetical order. James is asking about the difference between insert after and insert alpha. Insert after takes in a particular position in the list and always makes the node directly after that position in the list, as opposed to insert alpha that says, I will take the head of the list, so I'll take the whole list, I'll find the position that we should be inserting into here, and then I'll insert in the correct position. So it uses insert after it chooses which position to go into. So we get that kind of combo of using this function because it does a specific purpose, and using it with a particular position that we found, which is what this function does. Okay, let's go back to my slides. So we've got the insertion point, alphabetical insertion, and then we're going to go on to removing a player. So I'm going to talk a little bit about removing a player, and then we'll have a break, and then we'll write the code. Chicken's probably quite hungry, so we will... I don't know if you can see her there. I love that she just meowed for the camera there. So she was just sitting behind me on the chair there. Okay. Alright, Dean's explaining some stuff there. Okay, so removing a player. If we want to remove a player from the list, we're going to know which player we want to remove from the list because we're probably going to have found that player in some way. So we're going to have a pointer to the list. And if we've got pointers to things around the list, then we can decide how we're going to remove something from the list. So I'm going to show you the way this works. So let's say we have these players in this. Oh, this is the old example. I had an old example based on the fact that I've been watching a lot of Dragon Ball. This was when I was watching Dragon Ball. Now I'm watching Dragon Ball Z. So it's not that much different, but slightly different characters. So I had myself and Tom and Goku in here. And obviously, out of the three of us, Tom's getting knocked out first. So if I want to remove Tom from the list, the first thing I need to do is to say that I need to preserve this whole list. So the whole list must still exist, in which case me as the first player needs to cut this node out. So if this node's going to get removed, whichever node was before it, its next pointer needs to now skip that node. So that node needs to kind of get removed from the list in a way that leaves the list in its like proper legal format. So this section here is now a proper legal linked list, in that my next is pointed at another node, its next is pointed at null. There could be any number of nodes after this, but that's fine. So the first player bypasses the second player in order to remove them. Now, Liang's asking who killed Tom. Hard to say, but I assume that if myself and Tom and Goku are in a room together, then I'm not doing very much damage in the overall scheme of things. Alright, I won't get too much into questions. I think there's other stuff going on in there, but I'm going to try to stay on point here. James is asking, can you do a head next? Yes, you definitely can. So head next takes you, so this is head, here next, takes you to this node. If I was to go next there, then I would follow this next pointer and I'd get to a null. So yeah, you can definitely do head next. You can confuse the crap out of yourself by following multiple pointers at once. It's very dangerous, but you can totally do it. Okay, so at this point, the linked list is fine. The linked list has survived this. Tom hasn't. But he's still there in memory, and he's still connected to this player. Not super important that his next pointer is connected to the third player, because the thing that we're worried about is if we follow the trail from the head, we still have a legal linked list. But we have this node that's being removed, and if we're going to remove it, then we need to make sure that we can clean it up properly. So the next thing we're going to do is we're going to say, okay, this node and all its memory that's inside it now need to be freed. So if I call free on a pointer that's aimed at that node, that will give that memory back to my computer, stop me from getting memory leaks and things. I will end up with a complete functioning linked list here. This node will no longer be in the linked list because there's no next pointer aimed at it. And we have been friendly to our computer's memory by saying, here's the memory back. we don't need the memory for Tom anymore. This would be much funnier if he was here today, but he's busy doing other stuff. I think he's busy checking over the assignment. Like, there's lots of little bits of the assignment that he wants to make sure it's working. So, we've freed that node. I should have changed the names. Like, we could put Chicken and Frankie in here. I'll try to remember that for next time. Okay, so this node is freed, and then this is a functional linked list here with one of its nodes removed. So removing is a little bit less complex than insertion, because there's only one pointer that you need to change. You just move this pointer here to skip. So that's here. It was pointed at the second player, and then it points to the third player instead that skips it, and then we free that thing. There is still a little work we need to do there, right? We need to make sure we know which node this is, which node this is, which node this is. So we need to maintain pointers to things, but the theory of what we're doing is not super hard. Okay, I think that takes us to the break. Yes, it does. So we're going to take a little 5-minute break here. We will probably be feeding Chicken during the break, so I'll do the camera setup for that and everything. I wanted to talk about something that you could be kind of handy to you is a system called Git. Git is a way that we can save multiple versions of our code as we build it up. It's also a way for us to collaborate with other people so that everyone can edit the same code base, and it just sort of advances forward through versions, different versions, older versions, as people go through things. And it's definitely a professional tool that we use all the time. The majority of the backend that's running COMP1511 is running on a Git repository as well. So there are a few different ways to do it. GitHub and Bitbucket are two of the sort of easy free ones to to use. Excuse me, talking too much. Deeply ironic, I'm lecturing and I'm talking too much. These are pretty handy because you can keep backups of everything, but you can also go back through versions. So if you write something and you think you've screwed everything up, you can actually go back a few versions and say, okay, at some point I knew I had this working. And so you can go back through all of the times that you've commit's a keyword for these, your code into this repository of code that's usually stored on the cloud somewhere. And it's really handy to be able to roll that back and stuff. So it's pretty good to get familiar. You can start using these. One piece of advice I would give you is most of the time when you start one of these repositories, they start off as public, and so please don't label your repository really nicely. Say COMP1511 2020 term 2. Assignment 2, and then you start putting all your assignment 2 code in there, and then you get called up for plagiarism because you accidentally left your repo public and everyone else downloaded your code and submitted it. So if you are going to do this and you're going to put your current assignments on it and stuff like that, please make sure you don't have them as public repositories, because then we have 18 people submitting the same code, and it was just like, oh, this is really bad. And it's especially bad for the person who was just honestly trying to learn a new tool and made a mistake and made it public. So if you're going to do it for coursework, try to make them private. Okay, let's go on break. I'll get some food for Chicken, and then afterwards we're going to finish this example with with the linked lists and the Battle Royale. I thought I might set up the camera in advance so that when I feed her, you can see how she sings for her supper on the way in. Okay, I'm gonna go get her food. I'll be back.
Did someone just ask, is that cat food? Yes, it is cat food. It's like one of those things where it's like this scientifically formulated food for different reasons for cats. Chicken has hairball control food because she tends to clean herself a lot and then throw up hairballs, and so she has specific food that's meant to help with that. Alrighty, I'm gonna move the camera back up here. Yes, chicken is 9. I'm gonna switch to the other mode so I can move the camera without like giving everyone motion sickness. And then we'll get started again.
Alright, that's aimed back at me again. I don't really want to be that big. Chicken is 9 in human years, so she's actually a pretty old cat in the overall scheme of things. Luke is asking about the assignment live stream. Yes, it will be recorded, and I'll keep the recording on my YouTube. I will probably upload it to Echo 360 for everyone as well. Ooh. What just happened? I didn't actually press any buttons just then, so... Anyway. Oh, wait, where were we? We were... Okay, we're at the break, and we're here. Chicken's a she, and she's 9 in human years. Yes, I'm actually 1200 years old. Okay, so let us think now about removing players from a list. And we're going to go back to the idea of like, why are we doing this, right? Because this is a Battle Royale game, which means if it's a Battle Royale game, then we're removing players because they've been knocked out of the game. And so in order to remove players because they've been knocked out of the game, we're going to want to remove them by name. In which case we're going to want to find the name of a player in the list. So let's start. You'll note something that's happening with a lot of these is they tend to all be returning a player pointer. The reason why they're all returning a player pointer is because when we manipulate a list, we usually want to give back the head of the list. Giving back the head of the list might mean we're giving back a new list. It's not the list that it was before. Best example is when we insert a name like Anusha in this list, because she goes up the first element of the list, the head is not going to be the same head as we had previously. So at this point here, after line 36, I think chicken is the head of the list. And then if we insert Anusha into this list, she becomes the first element of the list. So the head is then pointed at her instead. This example here, where the old head was there, and then the new head is here because our new element is the first element of the list. Similarly, if we're going to remove a player from the list, there's every chance that we're going to remove the first player. If we remove the first player in the list, then the head of the list changes. So we need to be able to give back the head of the list. So if we're going to remove a player, we can do a very similar thing to this here, where we're saying, here is the name of the player we would like to remove, and here is the list that we want to remove that player from. So I'm going to copy that. We're going to come down here, make a new function, which says find a player in the list head that matches the input name. Remove them from the list. Return the head of the list. It may have changed. I should say that up here, actually. Returns a pointer to the head of the list. It may have changed. Well, that's true. That's more accurate. Returns a pointer to the head of the list. Okay. So maybe these comments, you can see how I comment my code is like it's a slowly evolving process as I say, oh, that's not as readable as it could be. I could make this clearer and stuff. And so stuff like this may change as I work on things. Okay. Same process, right? My processes don't change when I'm writing different functions. I think carefully about what I'm doing, and I will often say, let's think about what we're going to do. So first thing we do is loop through the list looking for a matching name. If we found a matching name, remove it from the list. Now, I could quite definitely think about making another function that removed from using a pointer. Hello, someone's just talking to me anyway, even after she's been fed. So I could have a remove player function that just removed a player based on a pointer, and I could have another remove player function that was just find player based on name, and then call them both separately. I think in this case, just put them both into one function, because I don't think I'm going to be removing players for any other reason, just for now. I'm not sure. I would be open to changing this later if I found another reason to do it. The beauty of code, right? It's malleable. It doesn't always have to be exactly what we write and we never change it, because it's a bit of a silly way to go about something when you've got it as flexible as it is here. Okay, so I don't think I actually need more than this. Those comments should be enough. So if I'm going to loop through the list, then I'm going to do my standard looping. So I've got a pointer, and I'm going to call it current. A lot of shorthand, a lot of people call it CURR for current. That's actually something a lot of programmers do. So you're probably not going to lose any style points for calling it CURR. I tend to call it current because sometimes I'm just like, oh look, we're so close to the word. It's like stir comp. If you just said string compare, you would have gotten away with that. So sometimes I just give it a full name like this. So struct player current is going to start off as the head. So we're going to start at the head, and then we're going to loop through the list. So I'm going to set up my basic loop here. So if current's not null, we're going to loop through, and in order to move between things, current is equal to current next. Okay, so this is a basic looping through the list. But what I would like to do is I would like to stop under certain conditions. So I'm going to say we're not just saying current's not null, we're also going to do a string compare. Oops, put a semicolon on that out of instinct. A string compare between the input name and the current name. Be careful with comparing something in a pointer that could be null. This only works because this gets checked before this gets checked. So if current is null, this string compare would never run. If I swapped the order of these two, so if I did this and put this here, like so, I would potentially have a huge issue, because this would try to access current and look at its name before checking that it's not null. So if you do it in this order, you can actually get into a situation where you're trying to access a null pointer, and you're going to say, look, I'm trying to follow this null pointer somewhere. and I'm trying to get a field out of this. And it's like, you can't do that. It's a null pointer, right? So you want to check it's not null before you do that. So I'm going to go back and put that the way it was. While loops will do this. They'll check the first one before the second one. And if the first one fails in an AND, the whole thing fails, and so it doesn't have to continue. So little trick there, that this will always happen in order from left to right. And it is important in this case because you cannot do this if you're not sure that it's not null. So we check that it's not null, then we check the name. Okay, so string compare can do this, but I want string compare to test against something. Is it equal to something? Is it greater than or less than something? So string compare is going to tell me that two strings are exactly the same. If two strings are exactly the same, string compare is going to give me a 0. So what I want this thing to do is I want this thing to stop on a 0. So if I say not equals to 0 for this string compare here, what I'm saying is if the names don't match, keep going. Keep looking through the list to see if you can find a name that matches. If the names do match, then we will stop. And the point at which we stop there, our current will be aimed at the thing that we want to remove. So when this loop finishes, current now aims at the node we want to remove. Maybe. That's if this makes it stop. What if this makes it stop? So if current is equal to null makes it stop, it means that the name that we're looking for is not in the list. So it either aims at the node we want to remove or null. So if current is equal to null, it means we got all the way through the list and we didn't find the name we were looking for. That's a possibility. So if it was in here and I said remove, what was that example? I had Goku before. Remove Goku from the list. It'd be like, well, Goku's not in the list, so there's nothing I can do there. So if we found a matching name, remove it from the list. Cool. So we've got a comment there helping us. Keyword if. Did anyone do like software design and stuff in high school and have to write stuff in pseudocode? I always laughed at that because it's like they had this really strong formatting for pseudocode. And it's like, that's the opposite of what it's supposed to be. Pseudocode's meant to be not code. So if the more formal you make pseudocode, the more you should have just been writing code. But this is pseudocode. So there's certain levels of pseudocode, and this is me going, this is formal and specific in what I'm going to do, but it's still kind of just English. But the keywords are the same. So you can see that I was already thinking about a keyword there, and then I was going to do something else. So you can kind of think of it like that, right? Like, so there is pseudocode in a sense. And some people get really formal about pseudocode, but personally for me, pseudocode's meant to be human readable so that we can then implement something. And so me saying, write your functions by putting the comments in for, I nearly dragged that whole piece of text somewhere else. By putting the comments in first and then fill them out with actual code, that's actually the practicality of using pseudocode to make good code. So yeah. So if you're wondering about what that pseudocode is, the intention of teaching people pseudocode is so that you can get into this process. And the process, the intention behind the process is you don't have to think about your algorithm at the same time as you're thinking about your code. And so if you can get it to that, then it's much better. Okay, so here, if we found a matching name, remove it from the list. So this I can test. If we found a matching name, I know that we found a matching name if current is not null. Oops, I just put another if in there. If current is not null, then we found a matching name. So then we need to remove the current node from the list. Let's have a quick look back at our diagram for removing something. So our diagram for the removing something had the first player, the second player, and the third player. In order to get the first player's next node to skip the second player, I need to know what the first player is. At the moment, my current pointer only aims at second player. If my current pointer aims at second player, I still need to know what first player is. I don't have any pointers going backwards, so I need to track this. Luckily, I've already built a mechanism earlier that allows me to track the previous node to the one that I found. So we're going to do a similar thing. So the same way that we had a previous node, and the previous node was going to follow the current, we're going to do exactly the same thing here, where we have another player pointer called previous, starts off as null, and when current moves along, actually, previous goes to current before current goes to the next node. So that way, yeah, it's this. So previous goes to current, current moves on. So you can't move the current first and then move the previous because you don't know where it should be. So previous moves to current, then current moves on. Now I will be able to use my previous pointer to be the one that skips over the current pointer. So the previous pointer would be aimed at this node, current pointer is aimed at this node, so I can change previous next to skip over this player. So I said I'm just going to, actually I could write this out if I want to. Skip current player, then free current player. I probably don't need this many comments, right? This is too much. I'm now commenting every single line of code, which is probably more than I need. But I'm just going to do it for now because we're thinking about it, right? So to skip the current player, I take the previous node's next pointer, and I make that equal to, so let's have a look back at our diagram so we know exactly what we're doing here. So I've got this one's next pointer, and in order to skip this, I want it to be in this position. So the first player needs to bypass the thing that's going to get removed. So this is previous. Previous next now equals this thing's next. So that would skip this thing. So if I copy this thing's next, so this is current, this is previous. So previous next should then become current's next, so that it makes that pointer there, which skips over this one, so it points at the same thing this thing was pointing at. So previous next equals current next. I probably don't need that. Actually, I'm going to leave it in case people are unsure of what's going on. Okay, so previous next is equal to current next. That skips it, which means the whole list is now reconnected around that node. And then to give that node back, I'm going to say free current, which is going to remove that. I know at the end of all of this, I'm going to be returning the head, but there's more stuff going on here. So there's more stuff that I'm going to need to think about at some point. At least I know that I can remove some parts of the list. Whenever I'm working with a list, and I'm thinking about the way that I could do things, this is going to work for any node. I'm pretty sure it's going to work for any node in the middle of the list. I'm pretty sure it's also going to work for the node at the end of the list, because it's only using previous and current. So even if previous next equals current next and current next happened to be null, that's fine, because I would just copy null into there, and previous next, the previous would end up being the final element in the list. But I know that I'm probably going to have a situation here for trying to remove the first element of the list. Let's test this with middle of the list and end of the list first, and then we'll see whether we can remove, we'll see what happens when we try to remove the first element of the list. Okay, so we come back up here and we start doing some testing. Okay, test removal. So let's print out, please enter the name of the player who was knocked out. Actually, I can make this much easier. Well, I want to type all of that, and then I was just like, the concept was actually much simpler than that. Who was knocked out? And then we are going to make a string and scan into that string. So let's make a string. I'm going to call it KO name, as in the person who's knocked out. and it's going to be an array, and because I have this hash define for the maximum size of names, I'm going to use the same thing because it represents a name. And I'm going to scan f into that. I could do an fgets or something. Actually, I might just scan f because I don't want the enter on the end, so I'm going to make this easy on myself and do a scan f into a string, and that string is going to get given the address. Remember, the and is the address of that array. So what it's then going to be able to do is it's going to be able to write into that array. Hopefully that will work. I'm pretty sure scanf with strings works like that. I mean, we'll find out in a second if it didn't. And then we will try to remove that player from the list using remove player. I actually didn't need to scroll down that far. It's right here. So we will say the head is equal to, because I know that we're tracking the head. So if the head changes after a remove player, we're going to replace the old head. At the moment, I don't think that remove player is changing the head of anything because I wrote the code and I'm pretty sure it's not changing anything yet. So we remove player using the KO name, the whoever got knocked out, and we give it the head of the list. And then we are going to print players of the whole list. And then we'll be able to see after we do that whether it actually removed the right players or not. So we're pretty sure this is not going to work if I talk about who is the first element of the list, but I think it might work for the others. So let's test this and see whether it works. So we're going to compile this. Oops. Oh, right. Okay. I thought that might be the case. Since this is an array, it's already a memory address. I don't actually, in this scanf, I don't need to give it a memory address because KO name is a memory address because it's an array. So this is one of those times where we don't need the and because this variable already gives scanf access to that piece of memory. So let's try compiling that again. Right. Let's run this. Okay, so a battle is running. Who was knocked out? So let's knock out someone in the middle of the list. Frankie's in the middle of the list. Who knows what actually happened to Frankie the Fox, but in this battle royale, Frankie the Fox went out pretty early. Good. Okay, I was like really confused. I was like, why is Frankie there? And it's like, no, that's the stuff I typed in. So Frankie has been removed from the list, and the list is now everyone else with Frankie remaining. Let's test that with another situation. So let's try removing the final element of the list, Tom. And the list gets printed out again without Tom in it. Okay, so that's pretty good. I know I can remove from somewhere in the middle and I can remove from the end. The thing that I know is probably going to cause us some problems, let's try this, is to remove Anusha from the list. She's the first element of the list. Explosions, badness. Okay, that's alright for the moment, because I know that I haven't dealt with that problem yet. So, basically Anusha's got invincibility shield at the moment. Cannot be removed from the list. Auto win of the game. So, we have used a pointer which was null. So current was null, and then we tried, previous was null at this point, and we tried to set previous next to something. That makes sense. Okay, so the situation, if we look at it here in our code, was that we tried to remove a player. Current was the head, previous was null. String compare matched with current, so this never ran. So current was not equal to null because current was equal to head. Previous was equal to null, and we tried to do stuff with previous. So if our previous is null, we're trying to remove the head of the list. So I think this is actually in here. If previous is null, oops, we're trying to remove the head of the list. If we're trying to remove the head of the list, we can't go accessing previous. So let's format this properly. That's an else. I'm pretty sure that I'm going to Control X and Control V there, and my indenting is all messy. Tab there. Okay, so my indenting is correct now. So I'm just gonna a standard list removal here. I might actually just get rid of those two, because the one thing should be enough. We're trying to remove the head of the list. So if previous is null, it means that we stopped this using this command on the first element of the list. We match the first element of the list. So if we're trying to remove the head of the list, then we need to do the tricky stuff we were doing before with the new head. So let's do that again. I'll have a pointer to the new head, and at the moment that's equal to the head, and I'm always going to return the new head here. So this is me saying that if I don't change this, then the list didn't change, but I may end up with a new head. So if the previous is null, we're trying to remove the head of the list, which means that our new head is going to be the second element of the list. So if we're removing the first element of the list, let's do a picture. We need pictures for this kind of thing. New picture, I won't save that. Okay, so here we go. Here we go. Just a simple list with not that many elements in it, for starters. And let's say that was, I'm just going to do ABC here, because I'm not going to bother spelling out names or anything like that. So what if I wanted to remove the first element of the list? So my head pointer is here. If I'm just about to destroy this thing, then I need to keep track of the rest of the list. So I need to make sure that I make a new head here. Right? So my new head is going to be pointing at the second element. How do I find the second element of the list? I find the next of the first element of the list. Okay. So the new head is equal to the next of the first element, which is head next. So now I can say my new head is the second element, which means that the first element of the list is no longer important. We don't need it to be able to access everything afterwards, because we have the new head of the list. Then we free the current head of the list. Actually, we could just free head. We can free head, or we can free current, because at this point we know that current's pointed at head. But let's free head, because I think it's going to be more readable to say we're definitely freeing the first element of the list, we're skipping over the first element of the list, and then we're freeing it. Then new head is now different. So returning new head, it allows us to say that the list has changed. So we've got several different possibilities here, right? If the current is not null, it means we found something. If the current is null, it means we went through the whole list and we didn't find a match, and so we go to the end here and we do nothing. We just return new head, which is head. So we give back the same list if we didn't find anything, yeah? If we do find something, so in here, I could say this, actually. If I'm inside this if statement, we definitely found a match. So I can sometimes put some comments in here to say exactly where I am within my if else's, especially if I start nesting them. Then we're trying to remove the head of the list, or I'm not going to say standard list removal. We're removing something that isn't the head. Yeah, so all the other elements of the list are not the head. And so we're going to remove things differently because of that. Actually, we could have put this free outside that, because it's the same free, but we won't bother with that. We're gonna leave it in there for now, because this is like our standard removal. Skip, then free. So you skip over the thing, and then you free. So if it's somewhere else in the list, you just skip over it. But if it's the first element of the list, you need to make the new head point at the new head of the list. So you need to say this thing is here, so that when we blow that thing up and it's gone away, I still have access to the start of the list, because the start of the list is now a different element than the start of the list was before. Okay, so this should have us freeing both removing and freeing someone from the list, whether they're at the start of the list or later in the list. Let's save that and test it and make sure that that case that we had there is not still a problem. Okay, so I'm compiling. Compiling's okay, that's lucky. And I'm going to run it. Okay, so let's look at who's knocked out. Let's go straight for the example that caused the problem last time. I keep getting freaked out when I see the name there, but that's the name I just typed in to remove them. Oh, you know what I'm going to do? I'm going to make this easier on myself. So print players. I'm going to do something like this. Players currently in the game. Because it's super confusing me to see the list of names, including the one that I typed in at the top. Okay, let's compile that, run it again, and then you'll see my output's going to be easy to read now. So players currently in the game. Who was knocked out? Let's try knocking out Anusha. Players currently in the game. Now it's clear to us that Anusha's been removed from the list. Good. Now we have the ability to remove anyone from the list, whether they're in the middle, the end, or the start of the list. So we now have the ability to this isn't a test anymore, we can actually use this code. So we could now loop through and remove multiple people from the list. So I'm going to call this the game loop. And what I'm going to do is I'll put that in here, and I'll say every time we loop through the game, we are going to print out who's in the game, we're going to ask who's getting knocked out, we're going to scan in who's getting knocked out, we're going to remove them, which gives the list a new head potentially, and then we're not going to print players again, because we're going to print it at the start of each loop. And I've named this thing a game loop, so I want this thing to loop multiple times. So it's going to be a while loop. I'm going to take all of that, put that in here, indent it so that it looks correct, and I'm going to say under certain conditions we're going to keep looping. So let me think. I want to keep looping until there's only one player left. I don't have a nice way of figuring out how many players are left. If I wanted to, I could loop through the list and count how many players are there, but I'm going to show you a trick. This is a cool trick. This function here, which is going to run every time we run the while loop, is actually going to tell me how many players are there because it loops through them all. So I'm going to do this neat trick where print players is going to turn into an integer function. It's an integer function, and I'm going to say returns how many players were printed out. Right, you see what I'm doing here? I'm just using this little trick because I know that this is going to loop through the entire list. So what I can say is let's have an integer called total, starts at 0, and every time I print out someone's name, I will add 1 to total, and at the end I'm going to return the total. So what I can do, this is where I'm starting to like build more complex code just to show you. You don't always have to use the complex code that I'm doing, but this is me kind of being able to use a function to do more than one thing at a time. So it prints players and it says how many are printed out. So what I can do here, okay, this is the cool stuff that I'm doing here. I'm going to take this function and I'm going to put it inside the while loop question. So, while print players is greater than 1, so while there's more than one player in the game, we're going to loop through. And then when there's only one player, or for some miraculous reason there's less than one player, I don't know how that could happen. Maybe if I didn't build up the list properly. This loop will stop when there's only one person left. And when there's only one person left, we'll be able to say, that they won the game. So there's only one player left. They win. Have an exclamation mark for winning. I'm going to do it like that because I know that I'm always going to print out their name, so I don't really need to say their name here. So what I should be able to get here is that every time I loop through, I will print out the number of players, and then I'll make sure that there's still a game running because there's more than one player. If there's more than one player, this loop runs, which means we will check if someone's got knocked out, we'll scan it in, we'll remove them, and at the end there's only one player left and they win. So let's save that and run it. Well, compile it first. And run it. And let's see if our game loop is working. Okay. Players currently in the game. We've got all these people. I'll just check. There's a whole lot of questions there. I don't know if Dean is able to answer all of those questions at once. There's a lot of questions about the assignment. That's okay. Johannes is saying, while head next is not equal to null. Yeah, you could totally do that. So you could do this without having to check that. So the candidate solution here is head next not equal to null, and then we can print out inside the list. So this would, assuming that the list started off with more than one player in it, this would totally work. If this list started off with no players in it, this wouldn't work because this would be a null. So at the beginning, it's a null. However, that is highly unlikely to happen, and so we could run with this. We definitely could. I'm tempted to, actually. Let's run with what you've got there, just to show that that works also. So if anyone else is looking at this, what I'm saying is, here, I'm saying head next is null if there's only one element in the list. So this is like another way to test this, right? Okay, so print players, we would still be wanting to print the players at the start of those, so that's the head. But now we're not as worried about the number output from that. So what we're going to do is we're going to print players each time, and I might call print players once at the end to show that when there's only one player left, we'll show their name there. Okay, so that was an interesting thing. I don't usually do it like that, actually. I built up this other way of doing it. Okay, so let's try running this now using that. Using Johannes's idea there. And we'll see if it works. I'm pretty sure it's going to work. I like the logic of what you're doing, but I'm never going to 100% say that something works until I test it. Okay. Time to hit the chat. Let me know who gets knocked out first, and I will knock people out in the order that the people type them in the chat. And if I don't win, I'll be very angry. Alright, who's going first? This is just based on latency and who types in names first. Oh, Frankie went first. So Frankie got knocked out, and I see Frankie's removed from the list. That's good. I got knocked out second. That is the first time that I've ever run this lecture where I didn't get knocked out first. Thank you, Frankie, for taking that hit for me. Although looking at that, there was a whole bunch of people who said Mark. I think 4 people voted for me afterwards. Then Dean goes after me, and then Anusha. Dean gets knocked out next. Anusha's next. Between Chicken and Tom, someone said Tom. No one wants to knock out Chicken. Okay. Players currently in the game. Chicken, there's only 1 player left. They win. Awesome. Okay. What we have done here. It took us a few weeks, right? Because we're thinking about all the different things we're doing here. Let's go back and look at everything that we've done. We've been able to allocate memory for a struct for a linked list. We've been able to loop through a linked list and print stuff out. We've also added some functionality to count how many things were in the linked list. You can do that, right? Anytime you loop through something, you can, you can get more information. Chicken's right here, by the way. She's just sitting next to me on my chair there. We have been able to insert using a pointer to any node in a list. We can insert just after that. And then we did a more advanced insertion where we were able to loop through the list and find where we wanted to insert something, then insert. We have also I've suddenly got a massive lag spike there. The stream's going to get a bit messy because I just got a lag spike. We have also been able to look through the list, find a player that matches this string, and then remove them from the list. Either the basic removal here, which is to skip over them and free them, or the special removal if they're the first element of the list to make the one after them the new head of the list and then free the old head of the list. So we've got all of this stuff that we've been able to do up until this point, which allows us to completely implement this Battle Royale player listing, I guess. So there's only one thing left to check. Have we definitely managed all our memory properly? So what I'm going to do is I'm going to compile this with leak check. Sometimes I forget the format. I'm pretty sure that's the correct format for that. We're going to leak check and then we're going to run this. Leak check is going to tell us if we forgot to free anything on the in the game. So if there's any memory we've allocated we haven't freed. So we're playing another round. Alright, so hit me up with names. We're playing another round. Who's going to get knocked out? Alright, I'm going to go through chat and see once the names start appearing, and we will knock people out based on the order that I see them in chat. Oh. Okay, as usual, I get knocked out first. It's always the lecturer that's like, it's like if I ever played games with you, I know I would just be like the prime target. Everyone would be like, oh, I killed Mark Chicken. Oh, Dylan knocked out Chicken. Oh, no. Hang on, I gotta spell that right, or else it's not gonna remove. Chicken got knocked out. Then someone said Tom got knocked. Someone tried to knock me out again. I'm already out. Dean gets knocked out. Oh my god, Frankie might even win this. Yeah, Tom's already out, everyone. I need a choice between Anusha and Frankie here. People don't want to knock Anusha out because, like, that only some of you know her. It's like she's one of the tutors. Come on. Make the... Oh, Anusha's out. Okay. So Frankie wins. Frankie, there's only one player left, they win. Ooh, error. Free not called for memory allocated with malloc in function create player in Battle Royale.c at line 59. Oh, I obviously had a bit of lag because chat's now going crazy. Live stream will be blurry because I'm definitely dropping frames. I'm just looking at my streaming there, and it's fluctuating a bit. I reckon it might be Netflix hour in my apartment block at the moment. Okay. So, leak check is telling me line 59. here. And yes, we know that because this is the only memory allocation in this entire program. But we do have an issue here in that there is still some memory that we haven't freed. There's stuff that we're leaving hanging there. So if we were going to keep running, we would have an issue that something was still there. I think it should be reasonably obvious which piece of memory is still not being freed, because there's always one person left in the game, right? So we could print it out and there's one player left. Every player is allocated with memory, so we still need to remove the memory for that one player. I'm going to do you one better than that though. I'm not just going to remove the memory for one player. I'm going to show you how to free the entire list. So I'm going to call this free list. It's going to be a void function because when I'm done with this function, there's nothing left to point at, so there's no point having a pointer. And it's going to point at the head of the list, like so. I have a diagram for this one actually. Where are we? Okay, looping to free the nodes here. So if I have a pointer here, and then I'm going to loop through the list. So I'm going to loop through the list and I'm going to free up all the nodes one at a time. Something I need to do is make sure that I don't free up a node before I've seen what its next is. Because if I just free the head, I'm not going to be able to free the second or third node because I no longer have access to this next pointer to get to them. So I've got to be careful and make sure that I can keep track of what's left in the list. And I've already kind of done this once when I freed up the first node of the list. So the code that was in remove node that removed the first node, we're kind of going to do that again and again and again to get through the list. So what we're going to do here is we're going to have the loop pointer. The loop pointer is going to move to the second node in the list. And then we're going to keep a pointer to the first node of the list here. And then we can free this one because we know we've kept access to the second one. So we save a pointer to the node behind the one we're at. So a lot of the times when we're looping through the linked list, we're going to do this double pointer movement so that we can have access to more than one thing at a time. Then we can free this one, and it's okay. It's okay to free this one because our loop pointer has already moved on to this one. So we can access this next one. And that would continue as well. The loop pointer would come onto here, we'd keep a pointer to this one, we'd free this one, and we'd keep going until our loop pointer hit null, and then we'd still free this last one here. Lang's asking, what if we leave an untethered bit of memory unfreed? Does it stay there forever? It doesn't stay there forever. Our operating system, once our program finishes running, is going to go through and throw away all the memory that we were using. It's actually technically called garbage collection in the operating system. But we want to still manually free all our nodes ourselves, because we don't want to be in a situation where we accidentally write code that still has memory unfreed. So even though this is actually just going to get cleaned up immediately by the operating system, we still want to practice cleaning up after ourselves in case, for example, we're making a program that runs for, a week at a time, and it runs this game over and over and over again, and it never actually finishes. Every time this game finishes, there's one person's worth of memory, and then it will slowly eat up, all the memory we have in our computer. So what we want to do is know how to clean up an entire list if there was some point that we needed to clean up an entire list. So let's say the game server crashes and we need to clean off the leaderboard at that point. We would call this and we could say, all right, clean up the whole leaderboard, and then we'll start fresh next time. Okay, so code to do this. This is the last thing I'm going to do. I'm going to run a tiny bit over time, but I do want to do this. Okay. Loop through an entire list, freeing all the nodes. So as opposed to in this case where I know that I only have one node in the list here, and I could just free the head, I want to make sure that we know how to free an entire list. Okay, so if we're looping through the entire list, we would have a pointer that we're going to loop with, and I'm actually probably just going to use the head. this time. Every other time I've used current that equals head, but I don't think I'm going to need that because I know that the head's no longer relevant. So while head is not equal to null, so if head's null, then I'm finished, right? I've already gone through the whole list. But while it's not equal to null, head equal to head next. So I'm doing a standard while loop thing here. I am going to need a previous pointer, so it's going to start off as null, and I'm going to do the same thing where the previous is equal to the head. So if the head isn't null, the head exists, then previous becomes the head, head moves on to the next one. Interesting thing here. What we've done in most while loops is the iteration to move on to the next node has always been the last thing that we did. With this one in particular, it's not the last thing, because if you look at this diagram, we wanted this pointer to move on while we're still accessing this one. So what we would do is we'd grab head next and make a copy of it there. So we're actually moving head to the next. And then we've got previous here, and then we're going to free this after we've already made sure we've used this in it. So we can't free this before we move head onto the next. We have to move head onto the next while we can still access it, and then we free the previous node. That's actually it. That's actually all the code that we need to do for this, because all this is going to do is it's going to move through the list, and every time it goes past something, it frees the thing that was behind it. And it moves past and it frees the thing that was behind it. And when it moves on to null, the final thing in the list, it frees the final node on its way past there. So let me just make sure that I'm not forgetting anything. Yeah, I had a slightly different way of doing it here, where I did it inside the list, but still works same way. So this is going to loop through the whole list and free it. In which case, I can now, here at the end of the game, before I return 0, I call free list on the head of the list. And I could have done this at any point in the game and it would have removed the entire list. But here we go, free list at the end. Going to compile that with leak check. Run it. Alright, one last time for whoever's still here. I've gone a little bit over time. Give me the order in which people were knocked out of this list. Okay. Oh, chicken got knocked out first. Wait, where am I typing that? Oops. I was typing it with lag. Okay, chicken got knocked out first, then Dean. Dean's not having a great day. Frankie got knocked out next. I lasted longer than usual. Then Tom, looks like Anusha's going to win this one. Yes. There's only one player left. They win. Oh. Error, free not called for memory allocated with malloc in function create player at line 61. 61 there. So that's the same thing, even though we're calling free list. Did I compile that? I did compile that. I wonder why there's still memory there. Am I freeing that properly? Pretty sure I am. Okay, interesting. So we're looping through. Head is next. Previous is where the head was. We're freeing the previous. I'm going to check my lecture slide code. That's the head. Head moves on. That's incorrect. That code's actually incorrect. That should be doing everything. Okay. Let's just check for certain. So if this frees the head, then what it'll do is it'll take the head pointer, and it's not null at that point. Previous will aim at whatever the head pointer was aimed at. Then head will go on to its next. So in the case where we only have one person next, this will make head null, and then we free the previous. So that should be fine. That should free it. And then we would loop again. Head would be null at that point, so we would then exit the while loop that ends that function. Yeah, there's an idea. Dylan and Taylor are thinking, am I actually freeing the final node in the list or not? Let's find out. About to free this person. I was intending to finish. I thought I was going to finish there, but I think we should debug this. And the string that we're outputting there is head name. Okay, this will give us a little bit of information about what's going on. Compile that with leak check, run that. I'm just going to go really quickly through this list. I should probably reduce the number of people that are in this now. Oh, it's between me and Tom. I'm staying in. About to free Mark. I'm the only one left. Error, free not called for memory allocated. Very interesting. I am, at the moment... Yeah, Jeffrey's saying... Yeah, Yuji and Jeffrey are thinking it is freed. Leon's saying start from scratch. I'm pretty sure this is just an issue with this. Or I'm not calling it properly. Free list, head, free list, head. I'm looping through using the head as the pointer. It's weird because there's only one player left, which was me. I was about to free that. I'm going to leave it here because we should finish the lecture. So if people have other things to go to, I don't know if there's a tutorial after this. I always forget. But there's also a help session and stuff like that. So I'm going to go into break mode, officially end the lecture, and then we'll come back and we'll have a look and see if we can debug this. And then we will, and then I'll answer any questions that people still have after that. So let's just officially end the lecture by going into break mode at the end, and then we'll come back and have a look at this. All right, be back soon. Alright, I'm back. I'm not going to take that long a break right now, especially because when this stuff happens, I'm like, what's going on? Alright. Someone said 2 hours later, still debugging. So I wrote my first code in the 1980s, and I'm still debugging. 30 years later, still debugging. Okay. And Lang saying I went on Stack Overflow to find out what's going on. Is the print test testing the right thing? Maybe. I mean, like, it's worth thinking about new ideas. Let's before we go for new ideas, let's try to get as much information as we can. So, okay, so this thing says it was about to freeze something. All right. So there's some information there saying we definitely went into this loop, which means we did these things, and we probably did this. But what I want to do is figure out whether whether there's something else going on here. So I'm going to do a printf here that just says, is there still anyone playing? So this would say that I have freed something incorrectly in this case. So I'm going to do print players of the head. And then this will tell us if there's still someone in there. Okay, I'm just going to ditch most of the tutors so that I can just do this quicker. If I get a name coming out here, then I'll know that I haven't freed it, even though I thought I did free it. Okay, so let's compile that again. One thing that I did there as well, when I changed the number of players, that gave me a little, like, what we call a sanity check sometimes, which is to make sure that I'm actually compiling the code that I'm running. This happens, right? This happens sometimes where you compile code that is not the code that you're editing. So I made an edit there that was really obviously going to change the way this worked, so I know that I'm actually compiling the code I'm editing. Because I could somehow have just been writing code and not saving it. So I'm going to take out all the pets. Ew. Weird. So, this is good. Use after free. This says that we tried to loop through a list and it was not null because we didn't set it to null. But we tried to use something after we'd freed it. And the thing that we tried to use after we freed is the thing that used to be called mark. Total was 0, which means it hadn't looped through the list. The head was still pointed somewhere in the vicinity of the memory that still said mark, because we hadn't actually overwritten that memory or anything yet. Which means that I was the first element in the list and I had been freed, because the use after free says I tried to use the memory that after it had been freed, which I shouldn't have access to. Sorry, I'm getting too excited, I'm not breathing. And so this means that that's being freed, which means there's somewhere else in my code that I am adding a player somewhere. So, create player is unlikely to call this more than once. It's going to be in insert alpha, I assume, because this is where all of the scary stuff happens. So where can this create player? Can you see it? Can you see it? I'm just gonna wait to see if anyone else can see this. Yeah, Dylan can see it. Yeah. So if I'm inserting at the start of the list, if previous is null, I create a player, and then I inserted a player after that. This should have been an else. This should have been either I insert at the start of the list or I insert somewhere else in the list. Not I insert at the start of the list and then I create another player randomly that just floats and never has a pointer to it and indefinitely creates a memory leak. This is the kind of thing that I did where I did that while loop of memory leaking. So what I've done here, oh, this is so insidious, right? It's just somewhere here in my code. This is exactly how you get memory leaks, right? This is exactly how you get memory leaks, by accidentally doing more than one thing, right? So if previous is null, this thing will create a player. It'll still be able to create a player. It just won't give you, it'll give you a pointer to it. And because I didn't track the pointer from it, because I assumed that inserting with the previous would link this all up, this thing was, every time I added someone at the start of the list, it was creating another copy of that person. But that was just floating in memory somewhere. It wasn't connected to the linked list, which means I could never find it again to free it. So the way that we're going to correct this is to say that when insert alpha runs, there are two lines here that will make a new player. Every time this thing runs, I can only ever run one line that creates a new player. Because every time I'm adding a player, I should only have added one. But I was adding two at a time. So I want to make sure that only one of these two options runs. I don't think I need that comment. So here, oops, I've copy-pasted too much stuff. I'm going to comment this differently. I often like to put the comments inside the if statements, because then you only read them if you're inside the if statement. Inserting at the head of the list. Inserting anywhere else in the list. Okay. You know what I really like? What I don't like is the fact that this happened after the lecture finished. But what I really like is we did some genuine debugging there. So I went through all the normal things where I said, okay, this is what I thought was happening. Let's check whether it's happening. And it appeared it was happening. And then we go back and we say, okay, the error has to be somewhere else. So let's look at the kind of the foundational reasons why that error might be there. It's always because we've created something that we haven't freed, and so then we had to go back and go, okay, where are we creating stuff? Okay, here we're creating something, there we're not, here we are, but it's simple. And then it was like, okay, here's the complex thing where we're creating things, and then we found it, right? So it's good. It's a good example. I mean, sorry, Jeffrey, but you can always go back. You can always go back and watch it. This will be recorded. Dylan's asking to go back over the functionality of COMP again. Let's. I hate those old C names. COMP. Sometimes I like to look at things in these web. Oh, this is just some random person writing tutorials. Still works though. Takes two strings and returns an integer. Compares two strings character by character. If the first two character strings is equal, the next characters are compared. So standard alphabetical order. You compare the characters, and if there's any difference between them, then that is the difference. But you start at the beginning, and you only go through, and if they're all the same, then you find the first letter that's different between them. Or a null terminator is reached. So, both strings are identical. It returns a 0. It returns a negative if the first character that's different is less than the second. Positive if the first character that's different is greater than the second. So, negative if the first is before the second in the alphabet. Positive if the first is after the second in the alphabet. Yeah. Cool, I think you got it there. Does anyone have any other questions? I mean, you can always go to the help session if you want one-on-one help with things and stuff. But I think I call that a successful, a kind of a successful run through a program, because we went through the whole roller coaster of like building things, all these different things, and then like bugs that we couldn't figure out and stuff. So I like how we ended up there. Yeah, Dylan, we'll talk about assignment stuff tomorrow. Liang, if we get A compared with a null terminator, I don't know. I've not tried that. I'm assuming that the empty word will be earlier in the alphabet than the one with letters in it, because the empty is vaguely considered to be a 0, but I'm not sure. Talking about people talking about going to the help session, Masony, yeah, Dean's help session is that. Jeffrey's asking why we did not have else in the first place. The reason we didn't have else in the first place is because I went quickly and just wrote code without being sure of what I was doing. Like, it's entirely me just going, oh, we need to check if we're the first thing in the list. If we are the first thing in the list, then we're just going to do something. And so I ended up making that mistake by rushing through things and not thinking about, oh, there's 2 alternatives. And if there's 2 alternatives, I need to pick one, not the other, not accidentally do both. Very, very hard to debug that as well, because that didn't come up at all until we figured out that those allocated variables that we'd been creating didn't have any pointers to them, so we could never free them. So I thought that was really interesting. Priya saying, is there anything we need to change in the main? I don't think there's anything we need to change in the main, unless there's testing. Oh yeah, this testing stuff. We want to get rid of this testing stuff now, because now we don't need this testing anymore, because we're pretty sure that free list is... Oh, we haven't actually tested this. We're so sure of ourselves, we haven't tested this. Okay, all of our fixes are in. All of our testing code is out. Let's see if this free list is actually going to work. Look, like we're still on the error here. We haven't actually tested. We're so, like, this is a very bad thing to do. Me just assuming that we fixed the problem, and then when we run this again, we're going to get the same problem, and then we're going to laugh, and we're going to go back, and we're going to debug it again. Okay, let's run this, and I think I might get knocked out first this time. And in an epic battle of Frankie versus Chicken, of course Chicken's going to win. Chicken probably wouldn't win. Chicken is way too cute to actually fight a fox. Leak check is telling us there are no more memory leaks. So, what we found was correct. I think we're good now. There's no more memory leaks. Yeah, and Leon is pointing out that the help session is through Blackboard Collaborate, and there's a link on the 1511 page so that you can get in the queue. You go into the Blackboard channel for the help session, hop in the queue, and the tutors will go into breakout rooms with you, one-on-one rooms with you, to help you with things if you need it. Yeah, Taylor's saying that the null terminator with ASCII value 0 might make that that way. Oh, you know what? We can just test this if we want. Let's instead of like trying to theorize about whether this works, we do have this machine right here that is going to do the exact behavior. So we have a thing that's going to alphabetically insert things. So what happens if we do this? So there's one that has no letters after it, and there's one that does have letters afterwards. Let's see what order these two end up in when we insert. You've already tried it, haven't you, Taylor? Okay, let's compile that and run it. It looks like the thing that has less characters, if they're all equal, the thing with less characters goes first. Let's make sure that that's not just the order that they were called. I don't know. I can't remember if my code was doing certain things, if they were equal or not. Yeah, they're ending up in the same order, even when I reverse the order that they're inserted. The alphabetical thing is definitely putting the shorter one first. Who else was there? Oh, it was me, wasn't it? Okay. Leon's got to go. See you later, Leon. Um, Jeffrey's saying coding's pretty much about tweaking it until it works anyway. Or you get a situation where you tweak it and it works less than it worked before. That's always a fun. Oh, right. You're just going, yeah, Sonic, gotta go fast. Totally. I quite enjoyed that movie, actually. Like, I'm one of the kids that played Sonic when it was released, so it was fun to have it. It was also funny because my partner's done a whole lot of work in CG. So she used to work for a film company, all this kind of stuff, and so we were poking fun at all the things because you know that they had to redo a lot of Sonic. So like, because like the initial Sonic had fallen into the uncanny valley and hit a whole lot of rocks on the way down and just really freaked people out with those weird eyes and teeth and stuff like that. And so we saw all of the shortcuts they made to still make the film and get it released. So it was pretty funny. Ooh, Priya, can we try typing a name that isn't a player? So let's see what happens when we do that, right? So it's actually running right now. Where's my mouse cursor gone? Okay, so let's try to remove Dean. Cool, that's not too bad, right? That's a good result. We want a result where if we type in a name of a player that's not there, the game can still keep going. So what I assume this has done is it's gone through the whole list for removal, and then it has said nothing matches there, so none of the removal code runs. Let's make sure of that. Remove player goes through the list. So current is going to be equal to null if it doesn't find it. So if current is not null, it would do something in there. Otherwise, it does nothing in there. Returns new head, and new head is just the head. So what it does, this is good. This is our removal code's nice and safe. It has said, I couldn't find what I was looking for in the list. Here, have the list back untouched. I didn't do any removal code and stuff. So that's a nice, safe way for our removal code to work. We don't want it to just crash or something like that. We don't want it to remove something else. We want it to just remove the thing that we definitely wanted it to, or nothing. Also, let's try to remove Chick. If Chicken had a child, it would obviously be called Chick. We know that we're not getting partial matches, so we know that we're safely not getting partial matches either. So none of these are getting removed with partial. I mean, if you get deep enough into assignment 2, then we put in some stuff like that for different string manipulation and matching and stuff like that. Yeah, so hopefully, Priya, that gives you some information that I think that we're doing pretty safe. Andrew's asking about lowercase. Remember, computers, lowercase, uppercase, completely different words. They are not dealing with lower and uppercase. We could if we wanted to. If we assume that humans are going to be using this with lower and uppercase and we want them to match, we could do something where we say, okay, before we compare names, set all the input name and the name in the array, make temporary variables of them, set them all to uppercase, and check those against each other, and then you check letter for letter instead of checking for specific upper and lower case. I didn't do any of that because, as you saw, I ran out of time as it was for the lecture. So I think if I'd added more string manipulation stuff in there, it would have just meant we were ran out of time. What's going on, Chicken? I don't know if you can see that little paw. See you later, Taylor. Okay, who else is... Lang's asking if I remember Sega World in the city. I do remember Sega World. I don't know if I ever actually even went there. I remember going through occasionally, but I don't know if I ever really had a good session in there or anything. And Priya's like, yeah, pretty epic accidental error handling. I didn't have a full intention that that remove was going to be able to deal with all possibilities. I only tested it for certain possibilities. So we're just lucky that it's like, if nothing works, then just don't do anything was a safe thing for remove. Okay, Leon's saying, somewhat off-topic question, but how does 1521 differ from 1511? Much more difficult or comparable? Very hard for me to say, Leon. I would definitely ask students that, because I haven't done 1521, and the course that I did that was roughly equivalent to 1521 was like roughly 20 years ago. So it's so far out of date that I don't think there's any direct comparison between my experience and what yours might be. Um, yeah, so I would say talk to someone who did 1511 with me in the last year and did 1521, or even just people who did 1511 last term and are doing 1521 now. You'll get a probably a better response there. CSC Sock is probably the best place to go to ask about stuff like that. As Liang is saying, Sega World was expensive. Yeah, I can imagine it would have been. Um, I can't remember if I ever actually went or not. It's too long ago now. Okay, one last call out to see if anyone has any questions. If anyone has any final questions you want to ask, type them in now, um, and I can answer them. Otherwise, we will be back tomorrow, same time. I still have to prep that. I just know that it's happening, and I'm going to talk about the assignment. So I've got some slides, but I haven't completed them. But I'll have that all ready for tomorrow. It's not going to be a full lecture worth of slides. It'll just be a bit to say, okay, here's the layout of the assignment, the marking scheme and stuff. It's not going to be that much different from the first assignment. But then I'll answer questions about things. Alright, lots of people saying thanks. I think that might be the end of it. Alright, thank you all. See you later. Chicken also says bye. She's just been sitting here on my mouse pad most of that time. And I will see you tomorrow if you're coming along tomorrow. If not, I will see you next Tuesday. Goodbye. I have a cat sitting on my mouse pad, so it's really hard for me to get my mouse across to the stop streaming button. Okay, there we are. See you later.